this talk is quite personal, so that's why I was like, why do I write proofs? So I always found, so this is Jean Chrétien, former Prime Minister of Canada, answering questions to a journalist about something, whether something he said was proven or not. He says, a proof is a proof. When you have a good proof, it's because it's proven. And I believe him. I'm happy with when you have a proof, you finished. You don't need to linger on. I don't care about the shape. All proofs are the same. I'm a proof irrelevance kind of person. However, coming up with a proof is the thing, and then this talk is about why do I do formal proofs specifically for the things that I do. So it's a bit of, there are two aspects to this talk. One is my thinking why I do the things that I do, and the other thing is because I'm presenting in this workshop that it's mostly about mathematical proof, I'm planning to give a bit of background on the theory of the things that I prove. So there's two aspects, so a bit of background and a bit of almost philosophy about what have I gotten out of the formal proofs that I do. An important aspect of my background is that I did my PhD at McGill with Brigitte Pienka, and there we were thinking about not as users of proof assistants, but as how to construct a proof assistant for proving meta theory of programming languages and proving things. So the formalism that we worked on was LF in a system called Beluga that is, if you're familiar with Isabelle, is closely related to Isabelle Pure. So the pure logical framework that Isabelle implements. But then I moved to Imperial to work with Nobuko Yoshida on the other side of the shop and to start using proof assistants to formalize proof about programming languages with behavioral types. So on that context, I will start with a very fast and short introduction to types in the context of programming languages and to specifically behavioral types. So typically, types are a tool that we use to classify the results of computation. So we say this program has this type because when it computes, it will produce a value of that type. So maybe it will be an integer, a list of strings, or a function from integers to list, or whatever it is. So we will formally, this is very obvious, we'll have some program and we will say this program has this type. Often we will let the program have dependencies on the context. So in this context, we will record things that have to be valid in the context for this type, for this program to hold this type. And we will define derivation rules to prove the type of a program. So for instance, if we have this program in which we call the function f on 1 plus 3, and we want to argue that has type not, well, first we will need that the context holds an assumption for f. So for instance, f is a function from natural numbers to natural numbers. And then we will use a typing rule that will say, okay, you need to know that the type of the function that you're applying is of this type. In this case, it's natural to natural, so it will produce a natural value. So this looks good. And then you will need to take a natural value. So we need to show that this is a natural number. And yes, because if plus, we can imagine that our language has a rule that says if the two operands of plus are natural numbers, the result is plus. So we construct these derivations and we say, yes, this computation should produce a natural number. But for this to be meaningful, well, the derivation is finished because these rules don't have any prerequisites. But for this typing to be interesting and useful, it has to have several properties. And the most important, and the one that I want to show in the slide, is that if we have a program with type T, and the program does some step of computation, then it has to be the case that the program that it's stepped to also has the same type. So if typing is not preserved by computation, then it doesn't say much. If we have a program that before computing has a type, it says, oh, it will be a natural number, but then after computation, it produces a string, then one would have to think about what's the value of having a type system like that. So it doesn't tell me anything about the end of the computation. So this is, you can think of this type system as a type system of Haskell or the type system of Coq or Agda. They all have this property. It's an important property, but then behavioral types is start thinking not only about the result of the computation at the end, but also the shape of the computation, things that happen in the middle. So behavioral types are useful for many things, but typically talk about the state of the computation as it progresses. So it doesn't just say, oh, at the end you get a natural number. It will say, depending on the exact discipline of behavioral types that you have, these things happen in some order. You can, for instance, it will ensure that you don't write to a file before opening it. So instead of giving an error at runtime saying, oh, you're trying to write to a file descriptor that doesn't exist, it will, at compile time, decide this kind of thing. So there are many different implementations of behavioral types. And these are just some examples, but type state is the one that has a state machine on the type system controlling things like, oh, you're writing to a file only out, after opening it and never again after closing it, and things like that. Binary session types that we will see more in detail soon. Binary session type says that if two programs communicate over a channel, it lets you specify a protocol. Multi-party session types is the same extension to the same idea extended to programs with many participants. And choreographies is a related, but it's not a typing discipline per se, but it's a way of specifying both the types and the participants of a multi-party session type. There are more examples. They are described in this book, Behavioral Types from Theory to Tools from 2017. And even since then, there have been other applications. But everything started in 98, at least for binary session types, when Honda, Vasconcelos, and Kubo proposed this paper in which they study a programming language based on process calculi. So think, if you are familiar with the pi calculus, this is a version of the pi calculus, but just made precise enough to have types. And the types are such that each channel, so there will be programs that communicate sending messages to each other. The messages that they are allowed to send or receive are specified in a protocol that is checked at compile time. So what they propose is a fairly complicated syntax. If you're familiar with the pi calculus, you will say, this is a lot, but we don't need to, I will highlight only the parts that we will discuss. Then to represent the concurrency, they propose, there's usually with process calculi an associated congruence relation that says, for instance, if you have two P and Q in parallel, then Q and P are the same program, because we are trying to model things happening in several concurrent orders. And the last piece for giving it operational meaning is a reduction relation. So it says when a message is sent, when if computes to a result, and so and so. The rules that binary session types proposes a typing discipline for this. So on the base, it has sorts. So these are the types that you more or less will be familiar from languages like Haskell. Would say if something is a natural number, if it's a string, a Boolean, and a session type, which is a type that says, oh, you might send first this message, and then you have a choice of these other messages, and then you will receive this message, and then you repeat everything, or maybe you end, and so and so. So the terms that I want to highlight to show a bit how these things work is, first, these are the two process term formers for first sending over the channel K, the value E, and then continuing like P. So this first process sends a message data, that is the evaluation of the expression E over the channel K. And then the second one, it receives data, reads data from the channel K and binds it to the variable X, and then it continues like P. So this corresponds to these two session types. First, read data of kind S, and then continue like the rest of the protocol, or send data that will be of sort S, and then continue like A. And the equalities, this equality will not be incredibly relevant now, but it will come up later in the first situation that we will think about. Processes are equivalent if they are alpha equivalent. So if you rename bound variables consistently in the binding spots and in the use spots. But then the important rule here is two processes communicates if one is willing to send on a channel and another one in parallel is willing to receive. So if these two processes, if this process wants to send E over K to this one, what happens is that when the communication happens, P1, this process continues like P1, and this one continues as P2, but replacing X with the result of evaluating the data. So nothing too surprising. So you want to send data, well, you evaluate it, and then you send it to the channel. The receiver will continue substituting away the variable X. So X is not free in P2 in the rest of the communication. So for this, we can, this system, we can have typing judgment that, well, for fidelity, I included both the contexts. In this context, you store both the variables of the process and the recursion variables that you may need, but it's a detail that we don't care. But the important thing is that P is typed by delta, which delta contains the types of all the channels that P knows about. So P might be talking through many channels at the same time. Delta will have the protocol for each one of those. And the typing rules, for instance, for send will look like this, in which we say that the type that sends, if the process wants to send, well, it's better that the channel, the type for that channel, channel K, is send a value of kind S. So here I forgot to say that E has to be of type S. That's what's missing, imagining it here in the premises. But if the process and the type line up, then it's okay if the data sent is of the right type, and the rest of the process can be typed with the rest of the protocol. So K might be a channel that is finished, then you don't get to use it again, but it might have more interactions that will be typed using these rules. But importantly, here we need to remove this action that has already happened if this part, when this is evaluated. So yes, this is there. So the theorem that we had before is, okay, we have a process with a type, and then it steps. The problem is that this is no longer true, because imagine in the case of sending that we just saw, if P was able to send because the type of the channel that it's using allows it to send, then after doing this communication, the type of the channel should have also moved on, because the sending, the shape of the computation, the part that says, oh, you have to send before receiving, or whatever it is, the protocol of the channel, would have happened here in the computation, but it doesn't happen on the type. So this theorem doesn't hold us trivially. Why? Because before we only cared about the result of the computation, so we were abstracting type over, it computes somehow a value of the right type. Here we want to say something about the shape. So the way we deal with that is, well, we do a labeled transition for P. So we reduce as we always do, but keeping track of if something was sent or received. So each transition will say what was the action that happened to make that transition, and then we type against, we say, oh, there must be a continuation of these channels. So there must be a delta prime such as if I do that action, then I can type with the new typing the process. So what happened was here, let's imagine P was about to send. Here the type let me send. Here I did the send of P. Well, here the delta prime would be the channel K has the protocol after the send happened. So this is the correctness theorem of this kind of this typing discipline. So with that background, so this is the type system introduced in the first paper for session types. So now is this paper from '98 has all proofs that have been that are well trusted and that have existed for a long time. No one doubts that this system with the fixes is sound. So why do I write proofs about this? So first, I am answering why I do these things, but none of these things I have done alone. So I have done all these things with collaborators that I want to credit and I will mention. But well, the first thing is, why do I write these proofs? Oh, because it's fun and I want to see if I can write these proofs. So that would be enough, but it's not as useful as an academic. We have the duty to make also useful things. So that leads to part one, which is to seek some clarity, because sometimes the things happen. So for instance, the paper that introduced binary session types, it was an idea that started a new field in programming languages. And it has, many people have worked on that, but the first presentation was not it was the cool new ideas, but they were not in the clearest way. This presentation has been evolved. The original presentation, in particular, of this paper contains some excitement that I will try to convey, but it contains some very delicate rules that confused very seasoned researchers and caused that papers clarifying that. It caused me to try to understand this thing using formal proof that we did in COC. So the original paper from ISO 98, but then when I joined Imperial for working on formalizing these things, talking to Nobuko Yoshida, she proposed talking about this paper that revisits the system in the original paper. And why did it need revisitation? Because the rules, people got confused by the exact presentation of the proofs in this paper. And then the motivation for this paper was that people thought that the proof in this paper was wrong, but it wasn't. And we will see exactly how. So the paper revisits this system. This is the system that we formalized. And there's a spicy rule, which is these two terms, which is instead of sending values like natural numbers or strings, what happens when a process sends another process a channel? So the idea of you can talk to this endpoint to do protocol. So if you're familiar with auth, it's how your browser tells Google tells a user to use Google or whatever auth provider to log in. So this is sending another process the knowledge of a channel. So now we are not sending an expression, but we're sending another K prime that is a channel. They use the term formers throw and catch. And now the types are, well, the data that I send actually has itself session type. So it will be channeled with some protocol that you send this, then you have the choice of these other paths, and each path would do something. So we have to now, it will be very important to remember that by definition, processes are equivalent if they are alpha equivalent. So meaning alpha equivalence, meaning if I change the name of bound variables, consistently. So if I have the identity function f of x equals x, then it's the same function as f of y equals y, because I change the names consistently. So here, the operational meaning of these processes say, listen, if you change the names consistently, then you get the same process. But then the rule for this is if you have a process that wants to throw or send a channel name to another process that wants to catch it, the communication happens. So the information is passed. But the things that happen here in the rule that are quite subtle is here, this process is willing to send information about the channel K prime. And the rule here bounds variable K prime in P2. And what you might expect is to have the same substitution that we have here. So here when we sent in the first case, when we saw the communication, when we sent, we told the other process, listen, I have sent you this data. But in this construction, we didn't tell anyone. Why? Because I can only send, according to this rule, K prime, if the other side bounds the variable with the same name. So if they're in a certain way, if they morally already know the name of the channel. And superficially, this sounds silly. So what's the point of me telling you you can use this channel to communicate under this protocol if you already know the name? But morally, this rule will be used after applying this rule. So the communication can happen only if you can alpha convert this side of the process to use the same variable. So this ensures that the variables are used soundly. However, if you're used to syntax as math has used bound variables since, I don't know, time immemorial, the name of a bound variable, if I know the binder and the place and all its scope, it's really not. I can write this thing, but this variable, because it's bound, I can rename it however I want. So this rule is kind of breaking some assumptions on how bound variables work. However, this rule works if you are able to convert this process, alpha convert it in such that you share the name, it works. Yes?
I'm a bit confused.
Good.
For alpha conversion, the K prime on the left hand, like the throw process and the K prime in the catch process, those are different variables, right? So I can alpha convert one without having to do the other.
Yes, you can, yes, definitely. Because this variable, so K prime is bound here in the scope is inside of P2. So these two arrows, this K prime was bound outside before. So they are definitely two different variables. But if you name them the same, you can communicate.
So if they were to be named differently, I could first alpha rename whichever side is inconsistent with the other one and then reduce. So I could sort of derive the expected rule from these two combinations.
But you might fail, so the communication might not happen if P2 already knows of K prime, and then you cannot do, K prime would not be free in K2, so you would capture it, so you cannot do. So this is how the rule says which processes can communicate and which processes cannot.
Both processes just use a fresh variable?
You could, but at this point, you don't have the binder for K prime.
Throw is not a binder.
This is not, it's bound somewhere before in time. So this is, that's the exact point. At this point, you painted yourself into a corner of the room and you say, okay, let's communicate if I can't do this part.
You have to alpha rename before wherever K prime comes from gets bound.
Yes.
Okay.
And this kind of breaks the idea that this is normal syntax, like in the lambda calculus or Haskell, or how you think about functions in math, and kind of makes this a bit wonky. So people didn't like this, but this presentation works for very technical details that the authors were very careful in checking. And this is another philosophical problem in which they were very careful defining this, but if you read the paper, they kind of, this detail didn't make it to the paper because of length restrictions. This is now another philosophical problem, is why do we did not make it to the paper if they spent time thinking about this? Well, space reasons, because it may be confusing, but then people found this unpleasant. So this is a new bound variable, so it should not be possible to compare it to this. If I get magic glasses that let me see syntax up to alpha equivalence, then there is no way that I can see if these two variables have the same, because this has any name that is consistently done. So people said, well, let's generalize it to this rule. I change the receiving end to a new fresh name, and then I substitute. And this rule looks very much like the rule we saw before, and this uses syntax in a pleasant way, and the stress that having funny syntax gives you was resolved, and this is what the revisited paper calls the liberal system. For a short while after the 98 paper on binarization types, people started using this rule because it looks much more beautiful. It looks like, oh, this is what they were really thinking. This more liberal system turns out that it's not liberal, but it's libertine, because it breaks the soundness of the type system. Now you can start with a process that it's well typed, do an action, and you get a process that cannot be typed, which is a very big no. Like, this is the whole point of the type system, was to never reach this problem. So what happens is that the understanding of the first one, that you get to communicate if you can alpha convert the receiving side, was lost, because this one always works, even if P2 already knows of K prime under because at certain point K prime is also in scope for P2. So this breaks subject reduction, and this paper that presents two systems presents the original, mentions the liberal system as not working, and presents a solution that we will not have time to go through. But the spoiler, the solution is, instead of thinking of channels, you think of endpoint of channels, because the error is confusing the endpoints of the channel. So the point where you send and the point where you receive, and which should have dual types. So sending on one side, it should be receiving. So this paper produces two systems for this. But even after this paper, if you ask people in the community, they will think, oh yes, the original paper had an error. It was not correct. And Vasconcelos, which is one of the co-authors of the first, Nobuko Yoshida, who started working on this very soon after, wrote this paper to say, no, the problem is with the liberal system. So for this, Nobuko, David Castro Perez from now contemporary, but at the time also Kent, I mean, at the time also Imperial, did try to represent this in Coq to show, okay, the proofs work exactly if you have this system. So we set out to do this formalization, so we call it engineering the meta theory of session types. And because you have many kinds of channels and variables, these things, our framework has uses locally nameless, which is a technicality, but the idea is that it has names for multiple disjoint nominal sets, so you can know this is a channel name and this is a variable name, kind of how on paper we say channels range between K prime, and then variable names are X and Y. But here you can literally separate these things using names from different sets that are disjoint. And the framework helps you reason about when a name is free and to do alpha conversion. Most notable, locally nameless, is a representation that has put the magical eyeglasses, and it cannot recognize the name of bound variables. It's called locally nameless because bound variables don't have names. Bound variables only say how far they are from their bounder. So a bound variable would say, oh, I'm the variable that was bound in the closest binder, or no, I was bound 2 binders ago. So you know how it refers deeply. So this representation can literally not understand, but every alpha equivalent term has exactly the same representation. So with that, we show first that the original system is not expressible in locally nameless or any term representation that quotients over alpha renaming. And it's not expressible because it collapses into the liberal system. And we show that the liberal system is broken, and it has a counterexample that it's valid because not only the types change, but worse, we have a well-typed process that becomes a process that cannot be typed. And we show the proof that the revisited system where we split every channel into endpoints is type safe. So this is the first proof that I want to talk about. And the idea was to understand and have a formal proof that how the community was, that explains these problems with the community. I had a very interesting discussion with Vasconcelos, who did the original paper, about how they came up with this very clever but very unusual use of binders in the original system. And his excuse was, yeah, we thought about it because it was a problem if we didn't do it, but we thought this would make it simpler. And on paper, it does make it simpler. But it makes it simpler for the proofs, but it doesn't make it simpler to satisfy people's intuition, because many people thought that the liberal system was literally the original system, and it's not. And that the liberal system is unsound, and that the revisited version with the nice endpoints works exactly. And it's in this case, the original system is, you have the idea, maybe you didn't get the most beautiful presentation. The revisited system, maybe it's not the most beautiful, but it's much more beautiful than the original one because it doesn't have surprises. So this work is very satisfactory in the sense that many people said, even the author of the original paper got some understanding, and definitely I got a lot of understanding, as this talk is very much about why I do things. So this was very interesting, even if I'm a bit frustrated that the original system has not been formalized yet, because the framework literally cannot represent it, because we cannot say an unbound name has to be the same as a bound name. Bound names cannot be compared because they exist simultaneously for all the appropriate renamings. So this was the first big proof that I formalized on a proof assistant, and this came from switching from the thinking about implementing proof assistants to using proof assistants. From this, we did part 0, we did have fun, and we wanted to extend it. So the natural extension is to try the next, a bigger system, but we wanted a justification. So why do we need to write another proof? So as before, I don't think we need to replace paper proofs because paper proofs anything. I think paper proofs are enough. They are, if they are reviewed and trusted by the community, they are proofs in the most Platonic sense. The one piece of anecdotal evidence that we have is we have many formalizations of many results in math programming languages and all kinds of aspects, and we have found preciously few errors in important proofs. So replacing with just a proof that the computer says yes, it's not interesting. It has, but the thing is that that's not why anyone does proofs, but because the formalization and the mechanization gives you insights. Like the first example was an insight that I got from doing a proof, but the second one, we set out to do something different. We set out to say, let's do the mechanization, but let's try to get something useful, because now we have a proof about a system. What can we use it for something? And people talk about the computational content of proofs, and this is exactly what we set out to do. If the proof says that if we formalize a type system, then we have a way of type checking using that type system if we write the proof in an appropriate way, that we can reuse then as a certified program that helps with that. So for that, we moved on to the next idea that we tried to do on formalizing session types, and we did multi-party session types. So very briefly, it's the same idea of specifying protocols between channels, but now the idea is that we talk about all the participants in the communication, not just point to point. Why people do this? Because before it's enough, you could have many channels. So I can have a channel with you, with each of you, and then you can have mutual channels among you. So why do we need multi-party? Because with multi-party, we can have global properties about our protocol. For instance, we can know that this protocol doesn't have deadlocks, which is a very important feature, that if we check only point-to-point communications, we cannot establish deadlock freedom of the whole protocol. But with multi-party session types, we can. So what it does, it's encode communications. Like think of these sequence diagrams from UML in some piece of syntax that we will call a global type. So it says A tells something to B, then B tells something to C, and then C tells something to A. In general, they are more complicated, but for the slide example, this will do. So this says how everyone A, B, and C have to expect to communicate in this session. And the interesting thing that we can do is that then we can implement each participant separately, because we can take this specification and project it to be from the point of view of A or B or C. For instance, from the point of view of A, this protocol means I will receive something from B, and then another communication that I'm not involved with happens, so I will not be paying attention to that. And then I will receive something from C. So from the point of A, I need to from the point of view of A, I only need to care about these two transactions. So the global type will be projected to all the local types, so each individual view of the types. Crucially, projection is a partial function. So sometimes a global specification might not be deadlock free, or might include someone not receiving a communication but having to know about it, which is not valid. So projection will fail when the global type is invalid, and we will not get the local types. But if we get the local types, then we know that the protocol is well formed and we can continue. And then we can use more or less traditional behavioral typing derivation to type each one of the processes. From the point of view of how useful this is, well, it's particularly interesting that each one can be implemented separately. So we could have a multi-party protocol with many parties, and then we agree on a global type, and then we all go away and implement our local view of the protocol, and then there will be a theorem that says all together they behave exactly like the global type. So this is for the syntax for those things. And now we will have a similar semantics in which we will say the local type has to be also able to do the same action of the process, and then the process will continue the, the same way. In our formalization, we go a step further and we say all the things that the global type can do. So we have an LTS that represents a global trace. The global trace is all the things, all the paths of concurrent communication that could happen in every interleaving from the specification of G. And then we do the same thing. We give operational meaning to the local types, and we get all the local traces per user. And the important feature, if this thing is going to make sense, it means that if we start from a global type, then the ensemble of local types should behave the same as the local type. So if we went away and we all implemented separately our programs, when we put them together, they should behave the way we discussed at the beginning. So the first thing is proving this equivalence. And then when we type processes with the local type, the process will also produce a series of traces. And we want this trace to also correspond to the other traces. However, we want a looser correspondence. We don't want equality because sometimes the process might not do parts of the protocol. So for instance, if you have a protocol for sending and receiving files, maybe your client doesn't receive files, it only sends files. So we just say that there's an erasure of the local traces that corresponds to the process trace, because whatever it does is valid under the protocol. Maybe it doesn't take some choices. Some clients might not do that. And we formalize this proof in Coq, showing that this diagram commutes. But in particular, one thing that, if you see the paper proof, G and L are syntactic objects. So are these equations that typically it will contain loops that you will unfold over and over. And you will have to prove many things about the unfoldings, and it becomes quite heavy syntactically. And syntactic proofs, which is mostly what I do, are already heavy and not exciting as more semantic proofs. So we created this co-inductive unfolding. So instead of representing the types as a piece of syntax, we represent it as a tree in which the unfoldings are just, well, it's represented as a graph, which the unfoldings are just loops, adding loops to the syntactic tree. And from that, we get the proof. The good thing is that we were careful about how to implement the processes in Coq to get that there are shallow embeddings of the processes in Coq. So we can use Coq extraction to get OCaml code. So we get executable code that Coq promises it's the same semantics as the Coq term that we extracted it from. We call this Zuid. And from that, we get many things for free. We can get programs that we can execute, but we know that if the original process was well typed, it follows the local type as we specified it in the proof. And because we prove that this thing commutes, we know that the semantics are exactly the semantics that we expect. And it was very exciting when we were writing the first examples that we run this thing over the internet and suddenly it worked as we kind of expected. And because one thing is having a proof and the other thing is saying it happened. So we saw it happen and it was very exciting. So notably, this part is by far the simplest part of the development. This proving this includes thinking about co-induction and all kinds of fun, clever proofs. But the processes, we had to be careful defining the type so that it's easy to extract. And after 5 minutes of thinking this part, then we could get all these things without too much effort. So the second thing that what I would say I write proofs is because it allows you to do these things. So now so it is a DSL for processes that follow global types, and we have a mathematical proof that they are composed together, they behave the same way that we said global types behave. So that is the second reason I prove things. And quickly, before I run out of time, is the thing that I'm thinking about now. This is not published, but there are two things that bother me of this typing rule. One is here, this rule is defined simultaneously by induction on the structure of the syntax of processes and types. So each time, and if you extend the typing system with a new way of expressing interleaving or things like that, then all the proofs kind of collapse and break because now you have new cases. And this alignment means that to make everything work correctly, you lose how many processes are typable. And the other thing is this operational semantics of types. It's only defined a posteriori. So we don't need it for all this part because it's only needed to be able to prove, because we want to say, yes, if the process did an action and the local type did the same action, then everything continues to be typable. But in the definition, we didn't use the meaning of computing with types. And the point of the things we are exploring now is use this definition on the typing. So the typing remains static because the programs are not executed, but we want to, as we type, execute the thing. So we drop that and we combine, we get rid of this in order to use the LTS during type checking. How? Well, if we are checking a process that will send data, we will type it to a G that we don't know, an object that might reduce with this action or not. We don't need to know the syntax, we only need to ask, can G perform the action that the process is about to do? If it can, we say, wonderful, so this prefix types, and then we need to continue typing the body of the process. So it remains static because at no point we execute the program itself, but during type checking, we will execute or run the semantics on types. So as long as we get a protocol specification that it's not too Turing complete, this typing relation should be decidable. So you can think of the syntax for global types, state machines, all kinds of things could be used as G because all our typing rules, all our typing rules depend on is never on the syntax of G, but on whether G can do an action or not. So we are formalizing these rules in Agda. And well, one more rule that I quickly mentioned is in the example that we saw, sometimes you are not involved in the communication of the global protocol. So you do your action and then other people would talk. So we need to add a rule for saying, if G can do transaction in which I'm not involved, then I will trust that they will do the right thing and I will continue with my, as if that had succeeded. And if everyone does that, the composite thing should be okay. And it should be okay because we need to prove that, which is the part that we haven't done yet. But to show a bit of code, this is Agda code. You don't have to understand everything. I will highlight the spicy parts. Implementing part of the typing judgment, but it's basically the typing judgment for these processes. And then we have the constructors for the receive and the skip rules. The key result that we want is that in the conclusion of all the rules, we never mention the syntax of the global types. So maybe we use global types as in the literature, or maybe we use state machines, or maybe we use, insert here your favorite representation of specification of protocols that will be well behaved, and we will talk about that. We only check that the specification allows for the actions that we need. And the use of ACDA is helping us because we need to find things like when are we allowed to do these things. So for instance, this predicate on global types of participants, it says that the global type is well isolated for G, which means if someone else does an action, P, the actions available for P before and after that should be the same. Because if I'm communicating with one party and I'm not involved in the communication of the rest, whether this already happened or this will happen in a second should not change what actions I can do before and after a communication that I cannot observe. So this is one of the aspects. So it turns out that getting this proof to go through requires sprinkling these predicates here and there, and proof assistants are the perfect way of having making solid steps in your proof, because you know you're not inventing something that 2 seconds later you will find wrong in your paper proof, and you get a computable thing that you can. We have a set of examples that we run each time, and we try to see if the type initial goes through. So the third use of proofs that I have found is it helps you clarify your thoughts in a way that is very interactive and solid. If your question if this is faster than doing it on the whiteboard 17 times, I don't know, but it's more fun. This is as much as I can promise. And with that, I repeat the three things. So the part 0 was to have fun, and we mostly had fun. There's always time in some fun activities like proving, which you are not fun. If you ask to go back in time and say, are you fun now? Are you having fun now? No, this thing doesn't go through. But eventually it goes through, and then it is really fun. The formalization helped me understand the subtleties of the original binary session types, and maybe even explain to other people things. And the very fruitful discussion I had with Vasco was very illuminating to me, and I bit maybe for him too. Formalizations can be thought of the foundation for formalized proofs. There are great examples of this. There's the CompCert, which is a C compiler that guarantees that the source code and the target have the same semantic. And that's a great example, but it's a lot of work to do this. My point is that sometimes it doesn't take a team of 20 people for 3 years to do a great thing. We did our small DSL that can do these safe programs. And the third thing is that interactive theorem provers are really interactive and are a way of clarifying your ideas and really help you find a nice presentation to your thing. Having said that, I thank you very much for your attention, and that's the end of my talk. Okay, one and one.
So you mentioned that the original binary session type system can't be expressed with locally nameless. So when you said that, I thought like, can't you do something like you keep an extra context that keeps track of the variable names, or maybe even sort of try to incorporate the variable names into the actual types, or like I guess you've proven that it's possible, or like.
Well, but I would I would, so that would solve it. But I would argue that it's not locally nameless because now you're remembering the names. What I want to do is to implement the original system using strings as names, like plain old names as on paper, to show that it is sound under the crazy rules. But using locally nameless, you will remember this name. It will slowly degenerate into the just keeping names of strings, I think.
Wouldn't it still have like the benefit that local names have, like in your mechanization, because you're kind of compartmentalizing that you can.
But the moment you do this, so you basically locally nameless keeps names for free names, and the bound names just are a natural number, no? So it's I'm 0 and the most recently bound variable. 1 is jump 1 and the next one should be me, and so and so. But if we keep a list of variable names, then alpha renaming should now start thinking, oh, like this will have impact for the alpha renaming to see whether I can do it or not. And I don't know. The real answer is I don't know. I suspect that it will be as much effort as using just strings as names, but it might not. So you might be up to something, but I'm not completely sure. But I would argue that if you keep names for the locally nameless variables,
It's not really
you were able to formalize it, but you will not formalizing it in locally nameless. So what I said, I think still, I still think it's true, but the real interesting question is whether that idea is better than having plain old names or not. So that's a good question. Thank you.
Yeah, I wondered, so your formalizations were in Coq and in Acta, were there any specific reasons why you chose those two? Or
So
do you make use of dependent types?
yes, we use all the things, but I don't think it's essential. So they could, for the binary session types, almost any proof assistant would have worked. For the second one, we would need co-induction. So maybe lean would be more work because it doesn't have native support from co-induction. So you will have to work a bit harder. But Isabel, Agda, Coq are more or less interchangeable. And for the last one, it's because I like using Agda, to be honest. It's very achievable in sure, like it doesn't use any specific thing. So the choice is, I don't think the choice of only after checking, like if you want to do co-induction, then don't use lean because it's the one that will make your life slightly more complicated. But otherwise, it's more or less not a big question, except little asterisk. For instance, for the extraction of code, it's easier to, if you want to get code in a normal programming language, let's say, and you accept my thesis that OCaml is a normal programming language, then Coq is good because it has this extraction mechanism. But in Agda, you could compile little Agda programs. I'm promised, I have never in my life compiled or run an Agda program. If it type checks, it works. Isabel also can extract to normal programming languages like OCaml or SML or even Scheme. So programming languages on the same club. So Isabel is also a perfectly good choice for, you could replicate every feature. If you chose Agda for the multi-party part, the extraction will be not extracted, but you will be able to run these compiled programs. But I would say yes. Of course, because we use dependent types, if you translate to Isabel, you will have to do it differently, but it would not be significantly harder, I think. Fundamentally harder, it will not be, definitely.
So for the first example that we talked about, you mentioned you formalize only the modified version, right? But not the original one, is that correct?
Yes, but no, I bought it the other way around, sorry. So the original one, because it's not representable in locally nameless, it's not formalized, but the revised one is, and we showed that the first one collapses into the wrong one if you use a representation that is quotiented by alpha renaming.
Could you gain some insights if you also formalize it first, or would it be?
I don't know how, it would be nice to be able to say, yes, the first one works even with the wonky rule. That would be satisfactory, and it would be closure. So I think yes, but not much further. I would not anticipate much further than that. Having said that, when I was writing this talk, I was thinking I should definitely try to write that using plain old names. And then I would have a more complete thing that I will have a good delta maybe for send to journal or something. It would be interesting to have this very complete formalization of binary session types.